okay.
Yeah, record on the cloud.
Yeah. Okay, the recording started. All right.
Thank you.
Yeah. So for question 5, this is how you write any number, and the number of different factors is this formula. Okay, now why is that? Well, you can think about it, right? So a factor is just, if I go here, a factor, what can a alpha 1 be, right? So alpha 1 can be 0, 1, 2, all the way up to alpha 1. Yeah, so those are the possible values for alpha 1. And then you can do the same thing for alpha 2 all the way up to alpha n. And because these are independent from each other, so you can choose whichever combination that you like. That's why you can multiply the choices together. So the first alpha 1 has alpha 1 plus 1 choices. And if you just multiply them all, you end up getting this answer. Yeah. So that's how you find the number of different factors. Now we can just do the question now, right? So which 3-digit number has the greatest number of different factors? So this question is about just balancing number of factors with balancing your having smaller numbers or having bigger numbers. So like an example is you could choose to have like 2 to the 7, but that only has 8 factors. While you might just sacrifice a few 2s to make a 3, but now you see how even though this number is bigger, even though this number is bigger, you see how instead of having 8 factors, you now have 12. So it's a juggling act. So I think the only method for this is guessing and checking, but you can always do it systematically, right? So if everybody's finished copying down, we'll go to the full page. So first of all, I guess to break up the cases, we have to check how many numbers there are. So can we have just 2 times 3 times 5 times 7? That's still small. That's 210. That's fine. However, if you get up to 11, that becomes too big. It's a 4-digit number, right? So we only need, we deduce that we only need 4 different prime factors at most. Yeah. So we really only need, there's 4 cases now. So at most 4 primes. Yeah. So now we just divide into cases again. So first case, we just have 1 prime factor. You always use 2, right? So it doesn't make sense to use anything bigger because it'll just make a bigger number, right? So you should always go for the smallest. So how many 2s can fit? 2 to the 9 is 512. Anything bigger and it's not a 3-digit number anymore. So number of factors is 10 factors. Okay, let's try 2 primes now. So we can have 3 to 2 to the power of something times 3 to the power of something. So in this case, you kind of have to guess and check. You could just start from big. So yeah, you can have 2 to the 9, but then if I make 2 smaller, so I go 2 to the 7 times 3, that's 384. You can't make anything bigger. So that has 16 factors. That seems okay, right? See if we can get any better. 2 to the 6. Can I get 2 to the 6 times 3 squared? That's 576, so that's fine. That's within the range. Sorry, let me just factors. This guy is the best for 1 prime. Okay, so 2 to the 6 times 3 to the 2 is fine. How many factors? We have 21. So this is even better, right? Now let's keep going down. to the 5 times 3 to the 3. Now, does that one work? Yes, it's 864. That's 24 factors. So even better. Now, let's just try 2 to the 4. We didn't get any more. We didn't get 3 to the 3, so that's obviously going to be worse. To the 3 times 3 to the 4. That works, but you see how at this point it's always going to be less than 24. So that's why we don't really need to check it. So in this case, this is the best. Okay, now let's look at 3 primes. So we have 2 to the something times 3 to the something times 5. Okay. So in this case, because you know that 3 times 5 is 15, so you start off with 15 already at least. How many more 2s can you fit? Well, it's around, if you divide 1,000 by 15, it's around 66. So you can fit 2 to the 6 because that's 64. So that will make it slightly less than 1,000. So the first guy you can put is 2 to the 6 times 3 times 5. That gives you 960 and a total of 28 factors. Okay, so instantly it's better than the 2 case already. Let's try. So you see how we're doing this systematically. So we only vary the number of 2s and then we look at the number of 3s and 5s, right? So that's a good way of making it systematic. There's a 2 to the 5. Because you're dividing a number by 2, you can't really add any more 3s and 5s because you'll make it too big. Okay, so 2 to the 5 will never work because you're basically just giving away 1, 2 for free without getting anything back at all in terms of 3s and 5s. The 2 to the 5 doesn't work. Let's try 2 to the 4. Okay, so now I can take 1 more 3, right? Because I divided by 4 and I can get a times 3, so that's completely fine. 2 to the 4 times 3 to the 2 times 5. That's 30 factors. So we're getting even more factors now. So like 2 to the 3. Again, at this point, you might look at it and see that there really isn't much choice because here, 2 to the 4 times 3 squared times 5 is 720. So even if you divide another 2 and you times by 3, it's already way too big. So 2 to the 3 doesn't work. You can try 2 to the 2 and so on, but you have to remember that the 2s has to be bigger than the 3s, has to be bigger than the 5s, right? If not, you can always find an equal or better construction, right? So if I say, oh, this is a good construction, if I say, oh, this is a good construction, then if I just swap the 6 and the 3, so if I just make it this, it's the same number of factors and this guy is smaller, right? So it's always going to be better. So this is another thing we can keep. We can go and say 2s have to be bigger than the 3s, than the 5s, yeah? So yeah, once you get down to 2s, it's way too small already. 2 is way too small, so it won't work, yeah? Okay, lastly, yeah, you can just check it. For 2s, the only thing it have is 3 times 3 to 2 and 5 to the 2. That give you 900, and it's close, 27, but not quite there. Okay, so far 30 factors is best. Now, last case, let's go with 4 primes. 2, 3, 5, 7. Okay, so first of all, 3, 5, 7 adds up times as 105, so you can only have 2 to the 3. That's the biggest thing you can get. You get a 40. How many factors? I get 32 factors. Okay, so this is the best by far, right now. If you go 2 to the 2, you can already see you can't get anything in return because even if you get 3 to the 2, it's too big already. It's a 4-digit number. And then 201 is pretty absurd because we already said the power of 2 needs to be the biggest to make it work. Okay, so after a long case bash, we finally end up with 32 is our answer. Okay, so yeah, a lot of AIMO questions are like this. There's always going to be a few per year, which is just doing a lot of cases. So you have to be systematic for it. And you have to find patterns. So here, even though it was quite a long question, we made things easy for ourselves by finding two patterns. Yeah. First of all, we just look at twos, and then threes and fives. We break it down, right? We break it down to categories. That's a very important thing in maths. And then the second thing we did is we noticed that the power of 2 has to be always bigger than the power of 3, has to be bigger than the power of 5. Because if it's vice versa, as you see here, you can just flip. You can just flip 2, 3 around, and then you end up having a smaller number and the same number of prime factors. Yeah. So that's another thing that really helped us minimize a lot of these cases. Yeah. So does anybody have any final questions about this? Okay. If not, let's go to lesson 2. Lesson 2 theory isn't hard, but there are a few questions which are quite tricky. All right, let's go to lesson 2 now. You guys can screenshot it if you haven't finished. Okay, let's go. So lesson 2 is about similarities. So there's two parts to this. One is this dilation. Dilation is a pretty niche topic. It's very useful for some questions in higher level. So higher level than AIMO. So you don't need to worry too much about it now. It's quite a niche topic anyways. Second one is similar triangles, which is very important for all of Maths Olympiad. Yeah. Okay, so first section of dilation, I won't ask you to do any of these exercises. They're all summarized into these boxes. So we'll just go through that and move on. Okay, so what is a dilation? Basically you have in a plane, you have a point, a central point, and then any other point in the plane. So this is my center point. So center of the universe, something like that, right? So center point, let's call it O. Center of dilation is what it's called. And any other plane, or okay, so you have to define a center and you have to define a factor. So it could be something like half or 2 or 3 or whatever. And basically what you do is once you define these things, any point like P, once you dilate it, dilation is a transformation. So if I have a factor of 2, I basically dilate it from OP to OP prime, which is double the distance away from O. Yeah. So it's a bit confusing, I know, but just bear with me for now. Yeah, so center of dilation, and then say I have a factor of 2. Any point P that's not from O, I will basically multiply its distance, right, by the factor. If it's half, so this is times 2. If I go half, it would be half the distance, okay? And they always have to be collinear, yeah? So, yeah. So you know how similar triangles is an example of this. So in this case, similar triangles, your center of dilation is O, and then something like P and Q will be dilated to P prime and Q prime with some ratio. The ratio is constant, right? That's why it's a dilation. It will always extend any point by the same ratio K. Yeah. So yeah. Okay, so that's basically the summary for this page. I'll give you guys 5 more seconds and then we'll move on to the other one. Okay. So properties that we can use for dilation is 1, collinearity. So just because it's a ratio, right? It's always going to be the same line. So that's just how we define dilation. And it kind of also makes sense in terms of vector-wise, if any of you have learned vectors yet. So yeah, collinearity is maintained. And because your factor is K, if you go from P to P prime, OP prime will be K times as big as OP, yeah? So in this case, if K is bigger than 1, if K is 2, you just double the distance. If K is half, you halve the distance. And an interval and its image is parallel. So we just define points so far. However, if you define lines, so it's basically what we did here, right? Up here. We can just say this line PQ dilates to line P prime Q prime, yeah? So lines can also dilate because you can just take the points, so P goes to P prime, Q goes to Q prime, and then you can just join both lines together, right? So that's also how you do it. So in this case, if I have a line P and Q, so this is another similar triangle, right? Now, in this case, what I did is a negative dilation factor, right? I did K equals something like -2, okay? So you can always do negatives. It will just mean that it's on the opposite side of O, so Q prime and P prime. And you see how they're always parallel because they're similar triangles, yeah? So the interval and its image are parallel. So QP is always parallel to Q prime P prime, okay? These things are pretty not useful. It just basically means that if you have different centers, there will be a different image. So something like that. Not quite useful because in Olympiad, usually most questions, it's already going to be a hard question if they have to use dilation. So usually you just use similar triangles. Harder questions will ask you to use dilation, but never dilation from 2 points. Yeah? It should really maximum be 1 point. So this isn't really useful. Okay. Let's just move on to similar triangles because that's way more useful. If you just generalize to a polygon, any similar polygon or similar triangle, you have sides in proportion and angles are equal. Yeah. So angles are equal and sides are proportional. Okay. I'm pretty sure you guys know how to do congruence and similarities, like how to prove these conditions. So I won't go through it, but please write in the chat if you need me to go over conditions for similarity and congruence. Yeah, I expect you guys should be familiar with it. So yeah, they do say here, they do give a recap. You have corresponding angles, and all corresponding sides. So you see how they always write it in the same convention. So this is just recap. So this is the similar sign. So triangle BAC is similar to triangle EDF. So you see how they always go the same, they always follow the same order. That's just convention. So you always write similar triangles. So you see how I wrote it this way. Don't ever write something like this way, right? Because you'll get yourself confused and you'll get the marker confused, and that's never a good idea, right? Always write stuff in so that the first of every triangle, the first letter of every triangle corresponds. The second letter also corresponds, and also the third. So B corresponds with E because they have the same angle here. Okay, A corresponds with D because they have the same angle here. This is just convention, right? And when we write angles are equal, we always follow the same order, right? So if I say ABC, this is 2, 1, 3, position 2, position 1, position 3. You say they're equal to position 2, position 1, position 3. So that's just convention. Yeah, always follow the order, never confuse it. Okay, so I'll just go through this quickly. Conditions for similarity. A, 2 angles are equal, you can just write this. So in school, you kind of just have to write this entire thing because they don't have any things, but Olympiad, feel free to just write AA. 3 sides are proportion, so you go PPP. P stands for proportion. So just like in congruent triangles, you have SSS, which stands for side. PPP stands for proportion. Yeah. Another condition is two sides and the included angle. So included angle just means same with congruent triangles. If I have these two sides, you should always use the angle in between. The condition is called PAP, proportion angle proportion, same as SAS from congruent triangles. And last one is IHS, so same thing as your congruent. You can just go right angle and any other two sides. That's the only time when you can use any other two sides is when it's right angle triangle. Okay, this should all just be recap. Most of these, I'll just do a few quick examples, but most of these are pretty easy, so we'll go straight on to the harder ones at the end. There are a few quite difficult ones at the end. Okay, so I'll just go through this quick example. I have FV is 8, BC is 12. So solutions, you should in Olympiad, you should always just prove it. So you can just go in AFE and ABC. Just go first condition. Second condition. Then you can say corresponding angles. And then therefore they are similar. So in Olympiad, you should, I guess, follow this as well as in school, right? But here I won't worry about it too much unless the question is difficult enough, for which it's quite a crucial step. For this, like for these triangles, it's quite obvious, so I might not go through it. I'll just state that they're similar, right? Because it's always the same pattern. It's always this angle is equal and this angle is equal for these types of questions. So I only go through it once. This is the time I'll go through. So yeah, this is the way you should set out your triangles usually. Okay, so now that you know they're similar, your proportion of sides is about 8 to 12 here. So they're asking you to find AC. So what's relevant is AE over AC equals to FE over BC. So equals to 8 over 12. Okay, so you can just say because they're similar triangles. And now we want to find EC. So EC is embedded within this, right? So I can just split it up. Of how to do this has a question. You just flip it and then you -1 to both sides. EC over AE equals to half. And then AE is 6, they gave it to you here. So EC is 3. Okay. So it's quite a straightforward example, hopefully. So except maybe the end where you have to do a bit of algebra. Okay, I'll give you guys another 10 seconds to finish writing and then we'll go to an exercise. We'll do a straightforward one and then we'll go on to the hard ones. Okay. Let's go with 15 first. Yep. So we'll follow the same system. If you think you finished the question, you can raise your hand. So that way I know when to go through the question. Only question 15. Sorry if I didn't say question 15. So I guess first hint is perimeter. So I'll just go to my notes now. So first hint is they only give you the length for one triangle, and then they give you the perimeter for the other one. So the thing you have to notice is it's fine. You can just determine the side ratio if you just look at the perimeters. Yeah. So what I mean is for a triangle, let's say the side ratios are 1 to 2. You can just say that you can know you see how all three sides are twice. So all three sides of the big triangle is twice as big as the small triangle. So that's why the perimeter is a ratio of 1 to 2. So you can just do the opposite, right? Because you know it's a similar triangle and you know perimeter is say ratio 1 to 2, then you can say all the sides and ratio 1 to 2, yeah? Because they're similar triangles and all sides are in the same ratio, okay? But yeah, first step, you have to prove that there are similar triangles in this diagram. Okay, so hopefully you guys have found this set of similar triangles. The reasoning is your common angle A, and they gave you 2 equal angles as well. So that's why these 2 triangles are similar. So yeah, can anyone tell me what the ratio of the perimeter is? Sorry, the ratio of the sides are? So hopefully you guys have found out that the ratio of the sides is equal to the ratio of perimeter, which is 2/5. Now can you finish with the rest of the question? If you think you have some answers, you can put your hand up or type it in the chat or whatever. No, I think people have had enough time. Okay, so once you have the ratio of sides is 2.5, you just see that AE is 2 times 5, 2/5 times 15. So the corresponding side of the similar triangles is AB. You see how AB and AE are corresponding sides. It's 2/5 times 15, which is 6. And then you're not having CE is just 19, right? Because you're given that AC is 25. And you do the same thing with AD. It's 2/5 times 25, which is 10. So your length of BD equals to 5. Oh, yeah, okay. Hopefully not, because the triangles are actually oppositely similar, so you can't have to flip the things around. Yeah. Okay. I'll give you guys an extra 5 seconds to write it down. Then we'll move on to the next question. Okay. Let's go to question 17 next. So two vertical poles, like 2 and 8, and you just go cross them together, and you just want to find the height of this. So it's actually quite a common question. It's quite a common tricky question as well. So in this question, the hint is you have to use more than one set of similar triangles. You have to use 2 sets. So you find the height of the intersection. Question 17. So can anybody just type in the chat? Can you just tell me 2 pairs of similar triangles you found? And the hint is these 3 are all parallel. So which 2 pairs of similar triangles you found? And yeah, if you've solved the question, don't be shy to put up your hand. Because if you don't, I don't know that you solved the question, and I might take longer to explain it. Okay, so please raise your hand if you finished the question. Okay, for those of you who haven't found the pairs of similar triangles, here it is. It's AEF and ABC. Okay, so anytime you have just two parallel lines and you have like two lines that join them, they're always going to be similar. Yeah? So a really easy way to see similar triangles is if sides are all parallel. Yeah. The other side, you also have triangle BEF is similar to triangle BAD. So those are your two pairs of similar triangles. Now see how you can manipulate the ratios to find EF. I'll just give you, it might be better to use algebra instead of lengths. So I don't know, it's up to you. So I see things more clearly in X, Y, and Z rather than just big fat lengths. So it might be the case for you too. Oh, okay. But yeah. Okay. So in order to use similar triangles with sides, you should always keep in mind that you should always, I guess, use the same length as much as possible. So I guess using DF over AD and DF over CB should be fairly obvious because you this is the thing you want and these two you already know the lengths. Okay, so which other pair of sides you want? Well, you should stick with the length with AB, right? Because they're the only ones that are related. If you go with DF FB and AF FC, they are not related whatsoever. So you'll never be able to get an answer from those. Yeah. So now that we know which ones to make similar, we can just go and have a look. So first one is AE over AB equals to EF over BC. So this is equal. And if we just go and use simplify into algebra, we might find it easier to see, and I'll show you why in a moment. X over x plus y equals to z over 8. So that's your first equation. And then the second pair of lengths we have is BE over BA equals to EF over AD. And that gives you y over x plus y equals to z over 2. Okay, so yeah, the reason why I chose to use x and y is here you can just notice that the left hand side, if you just add them together, both left hand sides together, you end up having 1, which is really nice. However, if I told you to add up the left hand side of this, you might miss it. So it's a lot easier to see it if you, I guess, reduce these lengths into algebra. Yeah, so 1 plus 2, 1 equals to 5z over 8. Okay, now can everybody type the answer in the chat so I know you're paying attention? Just privately message me. I'll give you 30 seconds. Just find what z is. I'm just checking to see if you guys are paying attention. Yeah. So what is z? What's the number answer? Okay. Good, one person so far. So what is z? George? Anybody? Okay, cool. So I think yeah. So z is just 8 over 5. Yeah. So yeah, I was just testing to see if you guys were listening or not. So yeah. All right. So you see how this question's pretty difficult, right? Because you have to find 2 pairs of similar triangles, and then even after you found both pairs and you made the condition, you have to notice that the left hand side, if you add them together, it equals to 1. And yeah, so it is personally, I think it would be easier with algebra, right? I mean, this is still algebra, right? It's just with lengths. So you see how if I look at this if I look at this and this, it's not easy to see that them added together as 1. However, if I use my algebra, x of x plus y and y of x plus y, it's pretty easy to see that adding together gets 1. Yeah, so that's how you do the question. Okay, so let's look at 18 now. What does 18 say? In the figure, AB equals to AC, so similar triangle, isosceles triangle, and then KL equals to LM. Okay, find the ratio of KB over LC. Now, seems really hard, right? Because there don't seem to be any similar triangles. Okay, so the first thing we have to do is find a construction. So can anybody recommend a good construction that we can use? No, so what I mean is, um, there isn't there isn't similar triangles here. So it's always a good idea to find a construction or to make a similar triangle. Yeah? So this question is definitely very hard. Yeah, so what I mean is if there's no similar triangles, you have to join a line or make a line such that you get similar triangles. So yeah, a lot of this is guessing check, but like once you get good at it, you'll make it. So can we make one between B and C? Well, that's already an existing line. So I don't know what you mean. You mean we can make a triangle similar to ABC? That that might be a good idea. Yeah. Okay, so yeah, that is a good idea. So somebody suggested that if we make a triangle similar to ABC, now how do we do that? There are few candidates. Or the most common way of making similar triangles is to construct a parallel line. Yeah, that's the most common way. There's only two possible things we can do. We can just do one that's parallel to L. Is that helpful? Well, no, not really, right? You didn't really get any good side, right? So does making one parallel to M work? So does making one parallel to K work? So we construct the parallel lines, and now something really nice happens, yeah? So you get a free pair of similar triangles, but we actually get another pair, okay? So this is a really nice construction. X. You might get the answer from here. Okay, yeah, so we just constructed it, yes? So I'll just write down the proof. Construct KA parallel to BC. Yeah? So this is a construction. You can do it, right? Because you're just adding in line. Right? And the reason why sorry, not KL, KX, my bad. So yeah, the reason why we did it is to make a pair of similar triangles. If you don't make a pair of similar triangles, there's no way we can ever manipulate side ratios. So then your pair of similar triangles. Oh, did I say AKL was similar to ABC? Okay, I'm sorry. It's AKX. Yeah, so my bad. But the nice thing about this is you do get another pair of similar triangles. See, you can find which one it is. Okay, so this is a really nice trick to the problem after this. So if you guys know the answer, you can type it in chat. So the two triangles are in 1:2 ratio. 1:2 ratio because oh, so I see what you mean. It's not quite obvious. Sorry. I will tell you why in a second. So yeah, it's not obvious. In this case, this isn't even needed, okay? So let me just tell you. Okay. So hopefully, once you look at this, you might notice it, okay? I'll just go through the solution now. It's quite a hard question. Okay, I'll give you 1 minute, but you should look at this pair of similar triangles. Okay, so the only reason why I guess we constructed it, right? So we do get a pair of similar triangles, but sometimes in geometry, the most obvious pair isn't the one that solves the problem, right? In this case, there is another pair here, and this will solve the problem. Hopefully, might look at. Yeah, they are both isosceles. You do not, however, know the ratio. You don't know the ratio. So somebody asked so yeah, no, they are isosceles. So these two triangles, AKX and ABC, are both isosceles, but oh yeah, sorry. The answer, yes. You got the answer right, yeah. But the ratio isn't, this ratio isn't 2:1. It's not strictly 2:1. But yeah, you got the answer. Nice job. Yeah, I'll go through the actual solution in like 30 seconds. Okay, let's go through now. So you have these two pairs of similar triangles, right? So I guess if you just look at the diagram, you might just guess it's 2:1, right? So if you draw an accurate diagram, KB over LC, you would yeah, if you can guess it's 2:1, right? But then often these guesses can help you find the actual solution. Yeah. So I guess how to think about the solution. If it's 2:1, right? What looks equal? Yes. So in geometry, it's always a good idea to draw these very accurate diagrams so you can just guess what's equal and see if it's true. Yeah. So if you can guess what's equal, what has some ratio, then that's often a lot of the motivation. Yeah. So this and this looks equal, right? It looks equal, but it is, but we don't know yet. But it's a good starting point, yeah, to know that those two are equal. So you can just tell that if once you can prove, so I'll just do this dream bubble. So you might think, oh, is that equal, right? And if that is equal, if XL is equal to CL, then we know that XC equals to KB, right? Is anybody confused with this? We know KC because we know XC equals to KB. Okay. Oh, okay. So why that's true? Well, from this, well, you do need this triangle. So once you get this, because you know AC equals to AB, because they're similar, you also have AK equals to AX, yeah? And then if I go AB minus AK, and then AC minus AX, I'm just getting BK equals to XC, yeah? So if you just look at it, if this is equal, then these two are equal, yeah? Because they're similar triangles. So does anybody have any questions about it? So yeah, XC equals to KB. Okay, I'll take the silence as everything's fine. So yeah, once you find it, then you see that the answer is just 1 to 2, right? Because you have BK goes to CX, and then your CL is half of CX. So that's why your ratio is 2 to 1. So now how do we prove it? Well, I already gave the proof for BK equals to XC. Now, how to prove XL to CL? Well, you might notice that this line extends to CM. So in fact, these triangles are actually similar as well, yeah? So KXL is similar to MCL. In fact, it's congruent. So if it's similar, you can go congruent. I'll just quickly write it this time. You have KXL equals to angle MCL because they're alternate angles. I'll just write it. I'll write it formally. So in triangle KXL and triangle MCL, yeah, these angles are the same because of alternate angles. You have this angle is the same. So XKL equals to CML, same reasoning. And you have KL equals to ML. Right, so often you could try to prove for similar, but then if I end up having a side that's actually equal, then you can just say it's congruent, right? So similar triangles are sides not equal. Congruent triangles, the sides are also equal. So I can, instead of saying, I can actually say it's congruent, right? Because the reasoning AAS. So now that we know it's congruent, therefore XL equals CL. Okay? So XL equals CL. Now, what do we want to find? We wanted to find what LC was compared to KP. So you can just go LC equals to half of whatever's there. So it's XC, and by 1, it's half of BK, yeah? Therefore, your ratio is 1 to 2. Other way around, 2 to 1. Okay, so yeah, quite a hard question. Like even after the construction, it's still a really hard question because you have to see the other pair of triangles, similar triangles, and also manipulate all of this. So yeah, a lot of this just comes down to practice. So yeah, we're going through the harder questions. Definitely after this class, try to go through some of the other questions yourself. You don't have to go through all of them because there are quite a lot of questions. Just whenever you have time and you want to do maths, yeah. So go back to the other questions and see if you can try them out. Yeah. So yeah. In terms of other constructions, yeah, so you might just be unlucky, right? And you might just go L. In that case, I guess the only thing you can try is notice that it's a bad construction. So it's quite a hard thing to do. That's why geometry is quite a tough subject. If you make a wrong construction, then you really don't know that's wrong until you try it out. So yeah. Constructions are usually good if they give you something else that wasn't intended. Yeah. So I intended to construct the red line in order to get this pair of similar triangles, but then I unintentionally got this pair. So that's a good construction, okay? Usually, if you get something else that you didn't intend to happen, then you should keep on going with your construction. Otherwise, if you cannot find anything else that, if you can't find anything else that you did with the construction, then you should try another one, yeah? Okay, I'll give you 10 more seconds and then we'll move on to, time's running out. How about we look at one last question? Let me see a nice one. Okay, so I hope you've finished writing everything down. Let's just look at question 19 as the last question, okay? So this question. Maybe next time, it's up to you. Maybe next time we can continue on doing these 3 questions, because they are quite hard at the end. Actually 21 shouldn't be too bad, but maybe 20 and 22. So maybe next time we can continue on with those. And yeah, we'll do the rest of this, like including the 5 questions. We'll do it next time as well. So yeah. So yeah, maybe for next week, we'll do 2022 and then the 5 AIMO questions. All right, but for now, let's try question 19. Again, you do need 2 sets of similar triangles in this question. So yeah. A good hint that I can give is midpoints as well. So often the nice pair of similar triangles is obviously the congruent triangles. So sides are equal, but then I guess midpoints of sides will also be equal. So triangles of ratio 1 to 2, because then you have midpoints of sides, and that's quite useful. So you see how they gave us a midpoint. So we're given that QU equals to TU. So that's a free midpoint. So what does it tell you about, let's say, PU and US? So any ideas of what they might think QV is? Have a guess. What does the ratio look like? Yep, it is. So yeah, good guess. It's 2. Do you know how to do it, or is it just a guess? Okay. Well, it should be time for me to go through it now. Okay, yeah. So yeah, the reason why I guess guessing is often good is because it gives you, it gives you ways to do it, right? You're basically just backtracking, yeah? So if you draw a really nice diagram, you might think it's about 2. And why is that useful? Well, basically, you're not having something like 2 and 1, and 2 and 1, because they're similar triangles, then you might think, oh, PU is half of QR, yeah? So similar triangles, because they are parallel, then you can go UP equals the half of QR. And now that just follows that U is the midpoint of PS, yeah? So this is just all we're thinking of, right? So U is the midpoint of PS, and now you solved it, right? Because U is the midpoint of PS, and then use the midpoint of QT. So yeah, that's how you kind of solve it, right? So don't worry if that doesn't make sense. I'll go through the actual solution now. So QU equals to TU. So that's given. So now this is actually a pair of similar triangles, congruent triangles, right? Because they're equal sides. So triangle PQU is not similar, it's actually congruent to triangle STU. So it's always good to put them in corresponding sides. So yeah, PQU is congruent to STU. And from there, you end up having PU equals to SU, yeah? Because they are corresponding sides of our congruent triangles. And now you see how we reverse engineer our answer for 2, yeah? Because if PU is equal to SU, now you know the ratio of triangle. Now you know the ratio of this triangle, yeah? So triangle PUV is similar to triangle RQV, yeah? But now that we know that UP equals to SU, now we know that the ratio is actually 1 to 2, yeah? By this guy, yeah? It's 1 to 2 because it's a parallelogram. So PS equals to QR, and yeah, because U is the midpoint of PS, then U is the midpoint of QR, if you know what I mean. That's why it's half of QR. That's how we get the ratio 1 to 2. Okay, so once we get ratio 1 to 2, then therefore UV over QV, so those are your corresponding ratio of sides of your similar triangles. So it's 1 to 2, but we know that QU is 3, right? So that's why UV is 1 and QV is 2, yeah? So yeah, these are quite tricky questions. All of these questions involve 2 pairs of similar triangles, and then you have to manipulate the side ratios. Yeah, so please do review it if you're not sure, but at least take down the notes so that you can review it afterwards. Yeah, I guess for homework, you can try out question 20 to 23 if you want, because we're going through those next class as well. Because yeah, these questions are quite hard. Anything beforehand, I assume that you should be able to, if you don't know how to do it, you should be able to look at the answers and know how to do it. Because these questions are much harder than what we had at the beginning. And yeah, section 2, you guys should have already tried out last week. It's okay if you didn't try it out because we're going for it next week. So yeah, if you haven't tried out, so we're just going to go through 2022. 21 should be fairly okay, but we can go through it next time as well. We'll just have a quick talk about area and volume, and then yeah, we'll go through these 5 next week. So yeah, try them out for homework if you haven't already from last week. If you've already tried it last week, then great, you have no homework this week. Just revise what we've done in the class. Yeah. Okay, does that sound good? Yeah, so before we go, I'll stop the recording now.